between data that we get or analysis that we can do from X-ray diffraction versus from EBSD and do some comparisons. So some of you have been asking me questions about textures from X-rays and when we should do EBSD and when we should do texture or when we should do X-rays. So this is hopefully to start addressing some of those issues. Okay, so start off with back to Bragg's law, which we've talked about a few days ago, and we know how these are done. Now, typically for X-ray diffraction, you're going to want to use a powder sample. So you want all the orientations there. You don't want any texture in your sample. And the reason is because you have diffraction only from planes that are aligned so their pole is aligned with the specimen normal direction. All right, so when you do a theta 2 theta scan, if you have no 220 poles lined up in the normal direction because you have a strong texture, then you won't get a complete X-ray diffraction pattern. If you do it from a textured sample, then you will have different heights and different peaks that may be seen or may be missing in your X-ray diffraction pattern. So we won't talk specifically about that, but let's just talk about measuring interplanar spacing using X-ray diffraction. It's a very simple procedure using X-ray diffraction, right? So you run a theta 2 theta scan, you get the various peaks from your spectrum. You come back to Bragg's equation, lambda equal 2d sine theta. The only thing that needs to be done is if you know what the sample is, you know what all the peaks should be, then it's easy enough to go in and index all the peaks, right? So this is a silicon, so it's FCC-like, so these peaks have to be all odd or all even. So you show them in the analysis that's shown here. Now it's actually silicon, so it's diamond cubic, it's not exactly FCC, so there's a couple of other things. You know, you have a 200 that's missing, but the 400 is there, for example. So it's a little bit different, but you can go in and you can check what these angles are. You can check the relative d-spacings of these, and from that you can back out what exactly planes are diffracting to give what peaks. Right? So we won't go into that part of the analysis. Most X-ray diffraction software is smart enough to look at where the peaks are identified and then say, okay, this is going to be a silicon oxide, some kind of quartz sample or something like that, right? So the software will go in and tell you exactly what it is. And the reason they can do that is because they can define these peaks. These peaks are pretty sharply defined. You can come in exactly in your data and you can determine what the angle of diffraction is. So 29.2 degrees or whatever, you can do it within fractions of a degree. Plug it back into the equation, calculate the d-spacing. The only thing to be careful with when you're doing this by hand is typically what's reported down on the horizontal axis is 2 theta. Right? So when you plug it into the equation, you divide it by 2 for the theta. Sometimes you'll just see theta there. It depends on exactly which system you're using, but typically it's 2 theta that's reported. But that's pretty simple. So you know what your X-ray source is, you know what your lattice spacing is, so you can come in and determine exactly what your d-spacing is for the various peaks. All right, so that's clear, right? How it's done with X-ray diffraction. So with EBSD, we have just these patterns to work with. We have diffraction from all the different peaks, just like we do on X-ray patterns, right? So we have all the different peaks, but the different peaks now are manifest as Kikuchi bands. And remember when we showed the diffraction, we showed that here's the D spacing, here's the planes that are diffracting. You have some diffraction coming off the top plane, off the bottom plane, so it diffracts at an angle of theta going up, at an angle of theta coming down as it's drawn here. So the bandwidth angle for any Kikuchi band is going to be 2 theta. Now remember that we have, let me get me a little pin here. don't know if a stylus will work on mine or not. Okay. So remember that we have this condition where we have the pattern center, which is normal to the plane of the phosphor screen. And it's a line, this Z star is a specimen to screen distance. It's a line that intersects the point where the beam hits the specimen. All right, so if we're looking, I can't do that, I have to actually draw. Okay. So then if you just consider a simple geometry, so this is your specimen, this is your phosphor screen. I should label this because drawing with my finger on a, it looked like a second grader drawing up there, but that's okay. This is specimen. Okay, so the beam hits, we have this position, whoops, that's just supposed to be a line. Maybe I should have used this one where it's more stable. So this point is the pattern center point, right? That's this thing. And then we have a band. I have shaky hands a little bit anyway. So I'm shaking and then my screen's shaking, so I got a double shake here. So let's say just in 2 dimensions that the band goes from a position here to a position here. Okay, so that's the Kikuchi band. Now, if I take a segment, so Z star is known, right? This is the specimen to screen distance. That's something that we've known, we've calibrated that in, or we can actually go in and determine it from the pattern, what that specimen to screen distance is. So this angle then, down to there, and down to there. Those are supposed to be straight lines. Those are going to be known because we know that the pattern center position is normal to the specimen, and we know what that distance is. So Z star is known, we know this point, and then we can measure what this distance is between the pattern center and the edge of the Kikuchi band. So then we can calculate this angle here, right? I'm not going to give it a number because, or a letter. So we can calculate that angle between the pattern center and there. We can calculate this angle between the pattern center and the other side of the band. So we know those 2 angles. So the only thing we have to do then is take the angle, the difference between those to find the bandwidth angle. So we can measure that, that's going to be 2 theta. Now, if we come back up here, the pattern center, if we have something like this where it's a silicon calibration specimen, the pattern center, hold my screen still, pattern center is around this zone axis. So that's a 411 zone axis. Okay. And so we talked about how for the silicon calibration sample, this band is a 110 type band. And so if it's a 100 silicon single crystal, so 100 is pointing straight up, then 20 degrees from that is the 411. So we can determine that. So that's pattern center. So now if we want to do a despacing of, let's say, this band here, then we can go directly normal to our pattern center and determine this is going to be where the bandwidth is. Now, the reason we need to go from the pattern center directly out isn't necessarily because of the calculation that I've showed you in 2 dimensions, right, to get the tangent of the angle, so then you know what the angle is. But it is because we have these bands that are not actually straight lines, they're actually hyperbola. And the only place where the bandwidth angle really makes sense is at that smallest position. And that's going to be at a position that is seen on your screen that's normal to the segment that comes for your pattern center out to the line. So let's say we're looking at this line here. We have to take a normal from the pattern center out to that line. This is going to be the point where the bandwidth angle is the smallest and where we need to take the measurement. Okay. So it's just a little bit of geometry you have to keep track of. But then as soon as you recognize that you're taking the bandwidth angle, you know, if we're starting to talk about that line, you have to come down here, normal from the pattern center. And then this is where the bandwidth angle will be measured, is in that position. Right? So that's clear enough? All right. So this calibration sample that I've drawn all over, that's an easy one if you just are looking at it and you want to determine what the specimen to screen distance is. Let's say we don't know the specimen to screen distance, but we know it's the silicon calibration sample, right? So we know where the pattern center is. So what do we do to determine the specimen to screen distance if we don't know it in a situation like that? Okay, rhetorical question. If you come back, I'm laughing at my pictures. If you come back to this two-dimensional view, now let's just draw a new one. Okay. Okay, specimen, phosphor screen. All right, that's pretty good. So, just straight line. So if the position here where the pattern center is, that's a 411 axis. This axis down here is a 111, right? So we can measure this distance between here, which is going to say, okay, that's where the 111 is, so we can measure this distance, right? So that's known. This angle is known, right? And we know it because we know this is 411, and we know this is 111. 1. It's a 1. Oh, that's not what I wanted to do. Okay, so that's a 111. So to determine the angle between 411 and 111, these interplanar angles, it's just the dot product, right? I have to make sure I normalize because I'm using integers for the directions. But as soon as I normalize, then I know the angle, this angle here, I'll just call it alpha just for fun. Alpha we get from, wow, 411.111. That's because it's cosine of the angle, right? So this is just a cosine. If I want to draw this whole thing out, a cos of this divided by the magnitude of 411.111. Okay.
How do we find this 411?
So how do I erase this stuff? There's got to be a way, right? Eraser, nice. Okay, so this is, we've said it's the silicon calibration sample. So we know this band that we've identified here is a 110 band. We know that this pole that's going to come and meet up here is the 100. And so then by a knowledge of what the crystal is, then you can come down and you can say this one is 411 in the point there. This one's going to be a 211 type. This is going to be a 111 type. Interesting. Okay, so 411, 211, 111. If we keep going down there, that's a 332 type. And all the way down further is going to be another 110. This is 110, this is 110. This one has threefold symmetry here, the 111. So this and this one, and this one, and the one down here. I could go back to laser pointer, I guess, and say this one, and the one down here are all going to be symmetric with each other, right? So 411, It's a 211 type, a 111 type. So we know that partially because of how we've oriented the specimen.
This work.
No, I've got one here. It doesn't work. No, I need my finger. I need my shaky finger. So, yeah, I should have. I was thinking that maybe I'd go to the software today, so we might, but that's why I did it on my laptop instead. Thanks, though, Sanisha.
Suppose is to find the pattern center. We find the pattern center, and from there,
Once we know the pattern center, then we can do all the calculations.
we can take any of the zone axis.
Any of them, yep, and we can determine what the relative distances are to the pattern center and figure out the geometry of the pattern. Yeah. So this is all done just with a click of the button, right? In the software, you can go in, you can take any random pattern like this, or any random pattern, you click the button and it will calibrate it for you and tell you specimen to screen distance and pattern center position. But we're going to get some practice doing it by hand, so I'm just making sure you understand what's actually happening. Okay.
Actual specimen distance is from the pattern center to the screen.
Right,
That is the normal.
right. So that's, yep, pointer. So pattern center is normal to the phosphor screen, and it's the point where that normal line segment intersects the specimen screen, the specimen beam interaction point. Okay. And it doesn't matter the orientation of your screen. Working distance could be way down here, then the pattern center would be way down there, right?
Working distance is horizontal distance.
I didn't catch that one.
But the working distance is horizontal distance from the.
It is the normal distance from the phosphor. So it's, in this case, how it's written here, it's not horizontal, right? So in this case, it is, this is a normal, it's kind of drawn on there that it's normal. It's got a backwards kind of normal sign. So this segment is normal to this plane of the phosphor. So if the phosphor was aligned in a horizontal position, right, then it would be in a horizontal line. Okay?
There is a very nice example in the book of Henry.
Yeah, there's a lot of discussion on calibration. I mean, Austin Day did his entire thesis on calibration for EBSD, so there's an entire thesis showing different techniques. And it's all based around the nomic projection that happens with EBSD patterns. One of the things he did, which was kind of educational, I think, on how the pattern is produced, is he took, let me try and draw this again, bear with me. He took and put what he called pawnbroker's balls. So it's 3 little balls that are in a different position. So he hung them off wires at the top of the chamber, little fishing line. So there's a little ball here and a little ball here and then a little ball over here. And so on the pattern, if you look at where the pattern was, let me try and do this again. No, laser pointer. Then he would get the shadow of those spheres, and they turn into ellipses because it's distorted, right? It's a projection that's distorting. So he would get a projection of those spheres that would go like this. And then if you take the major axis of those spheres, they're all going to intersect at the pattern center position. So that's kind of educational as far as how the projection goes and distorts the pattern along an axis pointing away from the pattern center. Right? So if I take the phosphor screen and move it in and out, all the positions on the phosphor screen, all of these are going to be moving to different positions, except the pattern center. That position is going to stay the same, right? Because we're moving on a line normal to that phosphor. So where that detector is, the point normal to that, if we're moving along that line that's normal, then that position stays exactly the same and everything else distorts around it. Right? That's the definition of that nomic projection. All right, so I spent longer on that than I expected to, but we're going to play with that a little bit in what we call the lab section. We're going to play with these patterns and try and figure them out. All right, texture measurements. So traditional X-ray or neutron diffraction texture measurements, how they are performed typically. You're looking at, let me see if I get my laser pointer up here again. You're looking over, your radiation is basically looking over a large area, or in the case of neutrons, a volume of sample. And then you get over here the detector, you're getting what is seen at that specific angle. And then you go around and you check what the diffraction is at all the different angles, right? So you start in the center and then you step around every 5 degrees as you're going out, and you just collect individual intensities at each one of these pixels in the little boxes shown on the point here. All right. Now you don't know anything about what the, this is giving me fits today. You don't know anything about where the space is that this diffraction comes from. So like this red spot that's being shown, you don't know if that red spot is coming from these specific grains, right? Like if you're mapping out an orientation map, you just know you get a certain intensity there. Okay, so just kind of looking what happens. Synchrotron radiation, you're looking through a volume of sample, which is spatially specific. I'm saying here it's low spatial resolution. They're probably down to 1 micron instead of 5 microns. Polarized light, I think we talked about these things before. TEM diffraction is very localized. Electron channeling patterns is resolution, again, about 5 microns or so. And then EBSD has an angular resolution somewhere around a degree for absolute orientations. Depends how well you can line up your specimens. All right, so for X-ray analysis, we come in, we measure a pole figure. So these are trying to show partial pole figures. You're missing the outside, right? You're missing the 90 degree, 80 degree positions. But you can come right in and measure the orientation intensities for each of these various poles, right? And then you come in and you worry about all the corrections that you need to do. So there's some mathematics that you play with to get the real measured pole figures, and then you calculate what the texture should be. So you're looking at 2-dimensional data, and then you're running through all the mathematics that's required, and you create coefficients for the spherical harmonic functions, and that's where you get this orientation distribution. Okay. We haven't gone through that X-ray calculation, but it's effectively just looking at spherical harmonics in these 2 dimensions from these different poles, and using those to pull out information for the 3D spherical harmonic. Okay, for EBSD, you're looking at individual measurements that are in 3 dimensions, right? So you're not just measuring the plane, you're measuring the specific orientation. From there, you can go into a binning procedure directly to calculate the texture, or you can use each of these to calculate coefficients for the spherical harmonic, generalized spherical harmonic expansion. Yes? How do you decide binning? So I have a little slides. We're going to talk about binning and smoothing again a little bit with Gaussian half angle. It's not easy to figure out how to do it exactly, because your result is going to depend, your quantitative result is going to depend on exactly how you do the calculation, right? In general, if I have a lot of data, then very small bins make sense to do it like that, other than the fact that it will take longer in calculation time. But for EBSD, the calculation's pretty quick, so it's not that big of an issue. But let's go through some of the things, and we can discuss it when we get to that part of the slides. All right, so texture calculation from X-ray, there's a number of different algorithms that are used to invert the pole figure. So one of them we call the WIMP algorithm. You can look up all these. And then the spherical harmonics that's used in EBSD. And again, we can calculate spherical harmonic coefficients from the X-ray data as well. All right, so here's an example of a couple of different specimens. So this is just material that was deformed to different positions. And you can look at orientation maps in these. This is a smaller length scale than this one, so a coarser structure in the 15 millimeter bar. So let's look at the 9 millimeter bar and let's look at what kind of data we get. So we can look at a various number of points. So in this bottom case, bottom right hand, taken 112 EBSD measurements, and they're all in different grains, right? So very big step size, and just take, okay, we're just measuring texture, so we don't care about grain shape and grain size, we're just measuring texture. So we do the same thing all the way up to where we get 150,000 points from 134,000 different grains. Okay, so these are just orientation maps, but they're orientation maps not to look at the microstructure, but to get the texture from. All right, so the X-ray textures, there's the 9 millimeter, 15 millimeter one. If we take the maximum number of measurements that we used for EBSD, about 130,000 for that 9 millimeter bar, we get a pretty reasonable correlation, right? They're not exactly the same. You wouldn't expect them to be exactly the same because of the question that you asked about how do we bin and how do we calculate and where do we truncate with our series expansion for X-ray and for EBSD both. But pretty representative. This scale, this is a multiples of a uniform distribution scale. So about 4 times random in the center is pretty similar for both of these, right, that we're getting. Okay. All right, so here's the difference if we go through from the bottom right. This correlates exactly with this chart, where you have the lowest number of points down on the bottom right and the highest number up on the top left. So this is the texture I showed on the previous page. Took about 13 minutes to gather these data, do the calculation. That was before 150,000 points. Now we're doing about 6,000 measurements per second. So it's very quick now, right? It's less than a minute to get this kind of data compared with 112 grains. Okay, so this one's obviously giving some artifacts or incomplete data. Right, but as soon as I hit maybe up over 1,000 grains, it's starting to look pretty reasonable to what the actual structure is. Right? Now this is something with moderate texture strength, has a 4 times random peak in the center, kind of moderate texture strength. If I had a really strong texture, if I had a single crystal, if we go to that, then all I need with EBSD is 1 measurement, right? That represents the texture if I have only a single crystal. For a random texture, completely random, maybe I would need to go up to 10,000 points or something before I got reasonable statistics instead of 1,000 like we did here. All right, so just a little bit of comparison of what we get from the different types of analyses. So we're looking now at this is the maximum intensity. So this was the 4 times random that we saw in the middle, right? So when we did the X-ray with the WIMP algorithm, we got right at about 4. Now if we start to play with different types of half angles and different types of bins that we're playing with, different numbers of grains, you can see that the values will be lower or higher as far as the maximum times random. But as I continue to go higher in number of grains, these tend to reach a plateau, right? And then out here is where we can actually determine this is what our bin size should be, or this is what our Gaussian half width should be, something like that. So the larger Gaussian half widths up here at 5 degrees and 2.5 degrees, they're giving values that are pretty close to what I'm measuring, right? If I drop down to 0, so where each point is considered a delta point where I don't get any spreading, then I have more difficult time getting the right calculation, right? So we need a little bit of Gaussian spread that we put on the measurements. This plot here we haven't talked too much about. It's the 45 degree phi 2 section of the orientation distribution function. And so this line along here is your gamma fiber, which is the 111 normal to the specimen direction. This line up here is going to be your alpha fiber. So typically with BCC rolling, you'll see a line along here and you'll see a line up here. And you might have different intensities as you come along here. And you see some differences, right, in what we're getting with EBSD versus what you get with X-ray. You see a little bit of differences. The character is still the same, but exactly how you do the calculation is going to be important. All right, so Gaussian half widths again. If n is really big, so that's the number of grains we're looking at. If we can do really big grains, then this half width usually we want to be small. This P is a measure of texture strength. And so if we have a really weak texture, this just goes from 0 to 1, from being really strong to really weak. So 1 is the weak part. So if it's really weak, we want a larger half width, right? So this is showing effectively what texture, what the p-value is in relation to what this half-width value should be. So if p is very small, then we make the half-width very small. If p is up here more of a random type of a texture, then we want these half-widths to be larger. And this is number of grains that we've measured. Say that again? Phi naught is the Gaussian half-width, right? Right. So that's an input parameter for your texture calculation when you're using EBSD to do the measurement, or single orientations to do the measurements. So all it does is it takes it, so if you have a measurement that's on the edge of a bin, for example, then the half width will spread that and put a little bit in the neighboring bins. So it makes it so it's not quite as discretized according to what your binning procedure is. Yeah, so that's half widths. Whoops. Number of grains, right. That's number of grains. Capital N is number of grains. P is a measure of texture strength, right? That's just pi. So. A measure of solid angle, is that what you're asking about? You're asking where this comes from?
Yeah, it depends upon all the number of grains.
Right. So if the number of grains is big, then we tend to look at smaller half widths. That's correct.
No, that is, look at smaller half width. So basically you are discretizing the reason of the observation.
So the calculation procedure for EBSD requires that you go into a binning procedure, right? So you put all the values in different bins, and you know the size of those bins is a parameter, an input parameter, and then the half width spread for each individual orientation is a input parameter. So we're just talking about what kind of parameters you might want to use to get measurements that are more in line with what we might get with X-ray. calculation.
So this is our actual decision, it's not the beam spread, means the band spread.
Okay, so the question's a clarification of, it's not the beam that's spreading, it's just in orientation space. So forget about real space now, we're just talking about orientation space. Instead of having a delta function for every individual measurement, a single point, we're saying that's going to be spread in some kind of a Gaussian peak around that in this three-dimensional space, right? So think of a Gaussian peak that is over this nonlinear three-dimensional space. So that's what's happening. And the half width of that peak is going to determine how tight your texture is, right? So if I have really broad half widths, it will tend to smooth out the texture. If it's really narrow and your bins are small, then maybe you'll have a very strong texture calculation. So this is, usually we just try and make this half width small. So my choice is I typically use 1 degree. I think the default in the software is 5 degrees, if I remember right. I think the default's 5 degrees. And I know Stuart Wright from EDAX that is, selling this OIM software. He will say if you have more than 100,000 grains, just use 0.1. Don't worry about the spread so much. Just make it small. So he says 0.1 when you have a lot of grains. I usually just do 1. Right? So will our calculations be different? Yeah, maybe a bin size of 5 by 5 by 5, which is pretty typical. Probably won't be too much difference. Maybe a little bit of spreading.
If you're selecting 1 degree versus 5 degree, your texture will be different.
Could be slightly different, yeah.
Initially, if we don't know, then how to make out?
So I would say, so the question is, how do we choose which half width to use? So I would say I would use completely dependent on the number of grains you have. And so if you're getting over 10,000 grains, for sure. If you have over 100,000 grains, then just make it small. 1 degree is what I use. Stuart would say 0.1 degrees if it's over 100,000 degrees. If it's more like 100 grains or 1,000 grains or something like that, then sometimes I'll use the default value just to kind of smooth things out a little more. And I do the same thing if I'm doing X-ray measurements or if I'm doing the generalized spherical harmonic, is I'll use a lower truncation value if I have less data. All right, so this is a measure of, we call it a difference ODF calculation. So it's basically a measure of how similar two textures are to each other, right? So if you take this function, this ODF measured by X-ray, this ODF measured by EBSD, and you subtract them from each other, right? So we're talking point by point. So every set of Euler angles through the space, every triplet of Euler angles through the entire space, you're going to subtract the value of 0, 0, 0 minus the value of 0, 0, 0, right? Euler angles. And then the value of 0, 0, 5 degrees minus the value of 0, 0, 5 degrees in the other function. So it's like the norm of a function, right? You're taking all of those, subtracting from each other, squaring them to make it positive, right? And take the square root, you divide that by the sum of the two, the average of the textures together, right? So this bottom one's just the square of the average, this is just the square of the difference, square root of the square of the difference. And so that's what's being plotted up here, this ODF difference. And so as you get to these values, right? So we've used different types of half widths, and as you're using different truncation levels for these, you can make them so they all pretty much line up exactly at the same position, right? Okay. Okay, so that's the last slide on that. Is there anybody have more questions on that? We've had a few questions as we've gone through. But you know, we're looking at truncation values. So this L value is in the spherical harmonic expansion, right? When you truncate, that's the one that goes 0 to infinity. So we're stopping it at some value. These are the Gaussian half-widths that we're playing with. Okay.
So if we have large number of data points, then we should have we can reduce the fragmentation.
If we have a large number of data points, meaning grains, different grains, then we can make a very small Gaussian half-width.
We can make it small one.
Right. We don't really need it then. All right, so a lot of people, when they talk about texture, they want to do volume fractions. So on this one, we basically say, you know, what's our distribution, what's our volume fraction of each. So if I have the discrete plot that's being shown here, so this happens to be a 110 plot, 110 pole figure, aligned up with this normal direction. So if I want volume fraction, I can look at the number of points that are lined up in a specific alignment within a given angle of that, divide by the total, and I'll get the fraction of points that have that orientation, right? So this is like a distribution function, right? That says within 1 degree, I'm going to have, you know, 1% of my data, and if I go within 10 degrees, now I'm up here at about 25% of my data. Okay. So that's what's being shown in this plot. It's just being colored on the pole figure, what we're looking at. 110s, remember, if you have it right in the middle, you have another one 45 degrees away, right? So that's what that's showing. Now, if we have X-ray measurements, or we just have the ODF, the orientation distribution that's being calculated, then the volume fraction is basically you have to integrate over a specific region of the data. All right, so you've measured it with X-rays, or you've measured it by EBSD, and you have this intensity plot. Then you don't have these individual measurements where you're counting them all individually. You just have these intensities of what the times random value is. But you can integrate over this space and say this is what I'm going to have for volume fraction if I integrate over that first 10 degrees, something like that. Okay, so here's looking at what the data look like. So the 9 millimeter specimen, the one with the smaller grains, if we have the X-rays, we get up here where from the calculation we get, and this is as a function of number of grains that we're looking at. So in X-rays, we don't have a different number of grains, right? It's just looking at a 2 centimeter square region, something like that. So we have the value that we get for X-rays for the 9 millimeter sample, and then the value we get for the different number of grains with EBSD. And then the same thing for the 15 millimeter one, which is down here, and then the EBSD data for that one. Since it's not a direct measurement using X-ray measurements, right? You're getting the intensities, you're going through the calculation and then back calculating through the integration of what the volume fraction is. You expect that that might be a little bit different than what we're measuring from EBSD, where we can just put bounds up and say, you know, that's 5 degrees and that's 6 degrees and that's 8.2 degrees away, and then that's included or it's not included, right? So there's the fact that the EBSD measures more precisely what the volume fraction actually is, but the X-ray does it with better statistics because we're looking over a larger region. So again, it's trade-off, and you know, what do you get for this? You know, X-ray diffraction is giving you about 21%. EBSD is giving you from about 32% to 26% volume fraction. These are just two different specimens. So just consider a small grain specimen versus a large grain specimen. 15 millimeter was the larger grain specimen. All right, so does it matter if we enforce symmetries? Yes, because the way that we calculate, the way we enforce the functions is dependent on whether or not we do the sample symmetries. So we look at our symmetries, and do we have these symmetries in the specimen or not? In this case, there's no sample symmetry that's been enforced. Do we believe that it should be enforced? You know, do we have a 6-fold symmetry on this, or do we have a 4-fold symmetry on this? Now remember, if we do a rolled sheet or something, we have this orthotropic sample symmetry. So this is just going back to what we would consider in doing the measurements. Do we have this symmetry? Is rolling direction the same as inverse rolling direction, or is, you know, the top of the sheet going to look at the bottom of the sheet, look the same as far as statistics? And then you can modify the intensity of your pole figure based on whether you're including that symmetry or not. Right, so we can force symmetry into these positions. So we take all the data, we force it into a quadrant basically, and say this is going to represent everything the same. So now when we play with that and we enforce the symmetry like it was done on the X-ray calculation, we look at the 9 millimeter and the 15 millimeter and what the values become as we are increasing the number of grains. Remember, the x-axis is number of grains. Now these things tend to line up better, right? Tend to get this better. And that's just because in EBSD we weren't enforcing sample symmetry, but in X-rays we inherently enforce sample symmetry. Okay. All right, so if we want them to match up, we should enforce that symmetry. Typically, I do not enforce it, and I go with the philosophy that I'm going to get enough grains that my texture is going to be represented accurately, and then I'll say the EBSD is the better measurement for volume fraction. Okay. All right. And this one says if you're above about 10,000 grains, you're going to be in pretty good shape. But remember, we have a 4 times random texture on this one. So if it's 2 times random, maybe we're going to want 50,000 grains, right? So it depends on texture strength. All right, so here's another example, a rolled sheet material. We're looking at maximum texture intensities, about 2.7 versus 3.1 times random on the maximum intensities of those. The features of the pole figures, similar. The details, different. Right? The details are definitely different on these. If we look at the orientation components along the gamma fiber and the 100 oriented or 100 rotated, right? So that's a Gauss texture there, that's a cube, and then back to Gauss. And then the fiber along here, which we say is a 110. So this is 100 pointing out, this is 110 pointing out, and this is 111 pointing out, right? So it's just showing where those are being represented. And in the orientation distribution, the 3-dimensional plot, you get more complete information, right? We show pole figures a lot because we are familiar with pole figures. But if you want to show the complete distribution, you're going to show it in the 3-dimensional orientation space. Okay, so X-ray pole figure, and then we're looking at number of grains that we're using. And again, up here in the top left is the highest number of grains. So this one, 30,000 grains approximately, which was 1.2 million points in this one, compared with about 212 grains, 200 grains or so down in this one. So again, the features are the same. You get above 1,000 or so, so that's close to 1,000. This is close to 2,000. You know, as soon as you get somewhere above 1,000 or so, they start to be reasonable intensity. Again, it's maximum of about 4 times random, right? 3 times random, something. So similar to what we had on the last representation. This is just showing a different texture with the rolled texture instead of the single fiber that we were looking at. All right, volume fractions, again, looking at different types, different components of the textures, right? So this part of it could be considered to be a skeleton line along the gamma fiber, showing the different intensities. X-ray is the black line. And then showing different numbers of grains. And these are surprisingly good, I would say. Surprisingly good to get these types of data. So a lot of people, should I use X-ray? Should I use EBSD? It's just kind of a trade-off of what exact information you're getting, right? You can make them so they look pretty reasonable. And then this is just different ways to calculate the function. So from X-ray data, we can use this WIMP algorithm, which is basically taking individual points and pushing them into a bin procedure like we do with EBSD. Or we can calculate using a generalized spherical harmonic expansion. So, whoops. All right. And then again, if we're showing the sample symmetry or not showing the sample symmetry, that's going to make a difference. Remember, we've talked about that. Okay. And then we look at these C coefficients. So we're calculating what the C coefficients are, and you can look at this J value, which we call a texture index. So there's a technique, I don't use this very often, but you can determine what the texture strength is by showing a single number, right? So instead of showing the entire distribution, you say this is the texture index, so you're taking 1 over 2L plus 1, that 2L plus 1 we see all the time in this expansion. These are just the C coefficients, or the coefficients for Fourier series expansion in the ODF. So we've determined these. We can come up with the texture index, come up with a value, and then we can plot what that value is. The bottom one here, the J0, that is if it's perfectly orthotropic, then this will end up to be 0. Right? And then we divide our texture index, assuming or checking if it's orthotropic versus what our actual texture index is. And that just gives you this value that's being plotted. So with X-ray, we're down here. So we get a specific value of 0.01 or so down here. For EBSD, it looks quite high to begin with until we get to about 10,000 grains again. Then it looks pretty good. So all of these data I'm showing you tend to point to the same answer, right? So if you say, how many grains do I need to represent my texture? If you have about a 3-4 times random, so a relatively modest texture value, you want about 10,000 grains. Okay. This is the same thing plotted as a function of truncation order, L, in the series expansion. So the X-ray value comes up here. And then the different plots here are showing how I've done the half-widths, which the wider half-widths on this case seems to match up better with this X-ray. And did we use... Doesn't tell us how many measurements we used on this one. I'm assuming we used a high number. And we still used a larger half-width to match that S0 value that we were calculating for texture strength. Okay. I don't know that this makes a lot of difference. We're just talking about filtering the data for bad data, right? So we're taking all of the data points. This is 1 million data points here. On this one, we're taking only those that are greater than 0.1 confidence, greater than 0.2, greater than 0.3. Remember, I told you that if we're better than about 0.4, it's basically 100% accurate for indexing. So these are all going to be pretty similar. Probably, even this, you know, they're all pretty good data, so it really doesn't change much through here. But if we have a lot of bad data, then for sure we want to at least filter out 0.1. And that is if we're just doing texture measurements. So we can't clean, you know, we don't have the grain shape, we just have 1 point per grain kind of thing. We're still going to be wanting to throw out those bad measurements. And then this is the same versus raw data versus how much noise we have in the data. We'll skip over that one. All right, what if we have clustering or if we have some kind of bimodal size? This is the same problem we always have with any specimen. What if our structure is inhomogeneous? If it's inhomogeneous over small regions, like over a millimeter, over millimeter scales, then we have issues of which box am I going to look at, right? Maybe I look over 1 by 1 millimeter, which is probably going to be a lot of grains in most materials, or we'll look over a different 1 by 1 millimeter section that maybe is going to be completely different texture, depending on what kind of clustering we have in the distribution. Now, we have the same problem in X-ray if we have clustering over centimeters, right? So one 2 by 2 centimeter region might look different than another 2 by 2 centimeter region. So that's what this is giving an indication of. In this case, it's showing some ferrite and austenite, probably just retained austenite in this structure. But you can see the clustering of orientation components that's being seen here. Yes?
So, the activity pattern for ferrite and the return austenite, though they are BCC and FCC, won't be, it won't come within that, the deviation that activity bands consider, and it won't be difficult to distinguish between these two phases unless we have a very high CI.
Yeah, so the question is, do we, for distinguishing between ferrite and austenite, which is BCC and FCC, we have to worry about a very high confidence index to be able to distinguish the phases. So there are 2 bands that are shared, right, between the FCC and BCC if we just look at the 4 lowest order, the 4 lowest index bands. So 2 are shared and 2 are different of the indexing bands that we're going to use. So they do overlap in some contexts, but typically, which I'm sure you know, the difference, it does a very nice job of distinguishing between FCC and BCC. And you can look at just the confidence index within each individual phase. So if we take a single pattern and we don't know which one it is, FCC or BCC, and then we look at the confidence index for FCC versus the confidence index for BCC, one of them is probably going to be around 0.8, 0.9, maybe 0.7. The other one will probably be around 0.2, 0.1, right? Because you're going to get a lot of bad bands in one of them. The one that's not the correct solution is going to have half of the bands are going to be bad because 2 out of 4 are different.
So is it like that because a long back I tried to do pattern and I was unable to do that even the pollution was great. And is it like that there are changes in the something in the software of capturing the USG patterns that now we can do it much easily and earlier we could not?
All right, so question is about in the past, he's had experience of where you couldn't distinguish well between ferrite and austenite using EBSD. So there is a little bit of difference in how patterns are deconvoluted. So if I have patterns on top of each other, how I deconvolute those patterns. But as far as just comparing FCC and BCC patterns, it should, if the patterns are reasonably good quality, you should be able to get a pretty good determination. Yeah. Right. Right. So they both have 200 and 220 type bands that are in the patterns, but then they have two different ones as well, and so that's what we rely on to distinguish between those two. If for some reason you're only getting diffraction from those specific bands, then it's going to be very difficult, right? If something's happened, if you have some kind of deformation where certain bands are going to turn fuzzy, we're not going to have good diffraction along certain planes, which happens sometimes depending on the dislocation content, then maybe something like that would interfere, right?
Recently we were doing some work on ferrite martensite, but ferrite is a martensite we can't, because both are BCC, BCT, or maybe martensite is also BCC.
Okay.
So that we could not.
Okay. Okay. Yeah, it should give reasonably good results, assuming the patterns are good and you have, you know, those bands that are determined or that are input correctly into the phases. So now you can put a lot more bands into the phases, right? You could put higher order bands and then it becomes more convoluted. And the other thing is with cubic crystal systems, I usually will use 7, maybe 8 bands maximum when I'm doing EBSD indexing. If you're using a higher number of bands, 12 or something, then you have a higher probability of getting some incorrect bands mixed in, which will lower your confidence down. So it's a little bit of, you know, how the system's used, but in general, there shouldn't be a problem in distinguishing between the two.
Maybe because sometimes the region austenites are thinner, as you have shown, and there is an interaction volume, and then bands from both grains comes together, and that makes the CI low, and then it index the most of the time ferrite, maybe, and that's why maybe not.
Yeah, okay.
This is very good.
Yeah, yeah, it looks nice. You can usually pick out retained austenite reasonably well. Okay, but you do have to worry about that as you're doing these considerations of what's my real texture, right? Anytime you have this orientation clustering, you have to have some concerns. This one specifically, you know, this boundary I'm drawing around here, you can look at it and say, well, maybe that's prior austenite grain, right? You could go in and make that determination. You can calculate if that's a prior austenite grain instead of just some kind of clustering. Okay, so I think we're an hour, so I think let's take a few minutes. Take 5 minutes. No tea breaks. No tea breaks. You have to provide your own drinks, your own biscuits. Yeah, so I'm going to talk a little bit more and then we can talk 11 when Sanisha starts chatting. And I might stop before then. I might stop at a quarter till, something like that, so that since we're stopping overall at 12:30, that would give him a little more time. So that's my plan.
on a different texture component.
Mm-hmm.
So how to calculate so actually I have already asked this question.
How to calculate the volume
Yes,
fraction?
yes,
Oh
sir.
yeah, that was one of your questions before, yeah.
So suppose that we have XRD VSD raw data. We have draw the we have measure the texture in the TSL software. So
Mhm.
TSL software, how to get the
Yeah, so you can put in fibers or you can put in individual components and then just say this is my tolerance angle. So show me everything within 5 degrees or within 10 degrees or something like that. And
TSL,
so, yeah.
TSL that is
Yeah, there should be something like that. Let me. One of the things I do is look and do some kind of a chart, let's say.
The volume fraction is equal to area fraction. Suppose the grains are in the part of the lake. Can we consider?
Yeah, that's principle of Deleuze, right? So volume fraction equals area fraction equals line fraction equals point fraction. So the assumption is that you have a random structure, which we never have a random structure. So assuming we have enough information, then that will be true.
Random in the size, random in the grain size. And so
Random distribution. So if we're looking at grain size, then random in grain size. If we're looking at texture, then random in texture.
also
Right.
means area fraction will be equal to volume fraction if the the depth is equal for both the faces. If the depth of austenite is equal to depth of the ferrite, and ferrite is also in the form of the lake, then it becomes equal. Then they will match.
Yeah. Yeah, yeah.
But if ferrite shapes are different, then austenite shapes are different, then maybe there is to be problem.
Right. Okay, so this is just a data set, right? Just an EBSD data set. And so let's say we want to know the volume fraction of, let's do a new chart. Let's say we want to know the volume fraction around a specific orientation component,
yes.
right? So we're going to go to a crystal orientation plot.
Yes, sir.
If we want to do a fiber, we're going to do a crystal direction plot. Right, so we'll do crystal orientation, and so we'll say, let's add a specific orientation, maybe 1, 1, and let's do, telling me I can't do that one, so something like this, right?
-110.
Right, so this is the texture, specific texture component.
Okay.
And then we're going to say, show me, just make them all blue, that's fine. Say okay. And we're going to enforce sample symmetry or not. Let's just not. Let's just say okay and see what we get. Okay, so now this is showing within 20 degrees. There are, 6% of grains within 20 degrees of that specific component.
Yes, sir.
Now let's do the same thing
Where it is shown? That
just on this
it is
plot,
shown the,
right? So there's the alignment within 20 degrees, and that's how much we have.
okay.
So now let's take this one, and let's do again a new chart. But this time I'm going to do a crystal direction chart, which is here. And then when I edit that, it's going to say, I'm going to add one. So now all I have is a pole, right? So let's say how much is within a given angle of a 111 pole. And you can plot this as a map, right? You can draw all the components that were within that distance or whatever. But then again, this is just going to be the same thing, but now it doesn't care about 110 being in plane, it just says 111. So how much is within what angle of your gamma fiber, right? So this is showing gamma fiber. So the gamma fiber, actually it's not much difference. There's not much gamma fiber on this one. This is an FCC friction stir weld, it says. But you know, if you come within 20 degrees, you know, instead of 6%, you get, is that 64% something? So 20 degrees is, you know, jumps way up there or something. So that's looking at volume fraction within a given angle of a orientation or within a given orientation of a fiber.
Yes, yes. That's the crystal orientation. It also gives the volume fraction of gamma fiber. Both are same.
This has been in your teaching, right?
This is just, the question was, how do you determine volume fraction of a given orientation component? When we calculate textures, I'm going to have this software up and we can just answer these questions. Maybe it looks like people are interested. Maybe we should just do this now.
Yeah, you should bring your laptops. You should have your laptops and you can do it.
Next time?
Yeah, you can do that because if you don't have the TSL, we can give you.
Sir, the
Yeah,
issue
give
with
you a
the-
demo version.
Yeah,
The
demo
issue
version.
with the TSL is the license, so you cannot calculate most of the things.
You can calculate on the demo data sets.
Yeah, but you cannot save it. You cannot save it.
Yeah, it depends which version. On one, you can do everything you want on the demonstration version sets. And on the other one, you can actually work on your own data sets, but then it will throw it away. It won't let you save it. So,
You can keep the older one. Older one is there, no? Older one.
Why sir, you are
Most of the things can be done.
explaining that.
so let's, I plan on stopping about 10:45 for Sanisha to get going early, since you said we're done by 12:30.
Yes, yes. So,
So-
you can start, right?
So let's just play with some software now. It's not exactly what I had planned, but that's okay. Let's do it.
Yes, let's play with the software.
So we'll just do this. And if you guys have it, you can follow along, and if you don't, then next time you can bring it and we'll do it.
Just have a laptop. We will give you an older version of it, which will almost work everything, except few new exotic things. What?
Yeah.
Can I study?
Yes.
So actually, I was doing this. This is my EDC data for the coating I'm preparing, electrodeposit coating. So since
We're ready? We're going? Okay. Okay, so we've had a lot of questions about some individual things that I've talked about and how to do things, and so I'm going to give you some examples. I wasn't exactly prepared to do this, but we're going to do it anyway. So let's see. So I have open, this is actually a demonstration data set from TSL. And let's just open it again here. So let's look at, for example, a small data set that is, I don't like these. Okay, let's do CVD tantalum. So I've opened the data set. I can plot up. Let's destroy this one. All right, so this map is actually doing something different than I expected. If it does it again, we'll just leave it. We won't worry about what the pictures look like. Didn't like that point number. All right, so this is a orientation map from directionally solidified tantalum. So the solidification direction is left to right, so it's growing horizontal. And the way it defaults is it's showing me the orientation, the pole, right here, pointing straight out of the specimen surface. And the reason I know that is because it says sample direction 001. So that 001 has nothing to do with orientation of your crystallites. It's not a Miller indices. It is just saying that the 100, or the X direction, is vertical on this, Y direction is horizontal on this, and the Z direction, or what they're saying 001, is coming straight out. So this growth direction is going horizontal. So really, if I want to see what the growth direction is, I want to plot something that would be in the 010 direction. So if I just go to properties of that inverse pole figure and say do 010, and we look at this type of figure, it's showing the the one axis is down, the two axis is horizontal, the three axis coming straight at. So now I'm plotting the two axis, and now it turns all red, right? So the growth started down here with a little more random orientations, and then as growth selection took control with the 100 growth direction, then it started showing that distribution. Okay, so I haven't done anything to rotate the data. I've just plotted it from a different standpoint. So now if I do just an individual pole figure of that, I just click on this and it says, okay, here's a 001 pole figure. Now, it's showing that all the 001s are horizontal. And then I have the other ones that are in some fiber. So this is a 100 fiber going off to the 2 direction, or the Y direction, right? Going horizontal the way this map was plotted. All right, so we've talked about calculating texture. Let's go in and see what we can do to calculate the texture. Now, right off the top, if we look at this data set, we have a problem, right? With calculating texture. Problem is, I probably only have 200 grains, maybe less, right? So I don't have very many grains. But I'm going to calculate it anyway, just to, because that's what we're going to do. Okay. All right. So I'm going to do a new texture, calculate that texture.
So you can put this online, right?
You can find this data set online, yes. Oh, we're not zooming it? Okay.
Why are you showing the whale?
I've noticed some people were daydreaming, and I thought a whale would be nice. It would be nice to help them cognitively. It assists with mindfulness, I think. Let's say that, mindfulness. Yes.
Just shall I say a few words there?
Oh, because we're online, that we were offline before?
No, we were online. Just to add a few words, that while we work in metallurgical systems, different systems, we always deal with certain kind of microstructures, right? And while we do deal with this microstructure, we usually take a photograph of them and show different features. But if you look even at the TEM micrographs, most of them are mainly qualitative. Okay? Unless and until you are taking a diffraction spot and letting it be small and checking the difference in the phase or orientation or something like that. Things have changed. So whatever metallurgy you do, we have to have quantification of everything, including the microstructure. So the main reason of proposing such a workshop is to enrich our scholars to get an idea of microstructure which is needed in a new age metallurgy, right? Not the old 1970s metallurgy. So everything changes and everything changes the way it is. So microstructures, we need to quantify every pixel, every point, right? Dave?
Yes, sir.
That is right.
That is definitely true. Yes, it's a lot of times from some of the old timers, they would say, here's a microstructure, and they show you a micrograph. And then they use descriptive material science, I would say, or descriptive metallurgy. Where they say, well, we have some flat pancake-shaped grains, and we have some elongated, we have some acicular structure, right? And they define the different regions. Here's some Chinese script precipitates in my titanium, whatever, right? So they use these terms that are non-quantitative, that are trying to be descriptive. But we try to move away from descriptive into quantitative. So that's a really good comment. Yeah, thanks. Okay, so we have a texture. Our goal right now is just calculate a texture. So we have different methods we can try, the binning or the harmonic series expansion. If we've calculated them some other way, we can plot them here just to compare. But we have basically these two options. We've talked a lot about harmonic series expansion. We're going to say, here's my truncation level. Right? This is that L equals 0 to infinity in the Fourier series expansion. So let's do 22. We have Gaussian half width. This is 5 degrees, which it defaults to, which for this data set is probably okay. Right? There's not very many grains. Yes?
Now you're selecting 22 or deselecting the 16. Previously you showed 16 and 22.
It was at 16, and I just selected 22? Oh,
No,
okay.
my question is how to decide?
How did
How
it?
to decide this truncation, whether to select 16 or 22?
It's just whatever was done before is going to come up, and so then you have to decide what it's going to be, and it's the amount of smoothing. So if we have more grains, so we don't want to smooth as much because we have enough data to fill in everywhere, then we want a higher truncation value, right? Because that will give a more accurate measure. If we don't have very much data and we want to kind of smooth it out so it looks reasonable, then we go to a lower truncation value. And that's the same with the Gaussian half width. Yes, another question.
Number of grains. Whenever we are taking the data set, we get number of points. Like, so how is it that how much grains we are actually having in the problem?
Okay, good question. So the question is, when we look at our data set, we're talking about a specific number of data points. And we want to know when we're talking about texture, we're talking about a specific number of grains. So how do we know how many grains we actually have, right? So remind me of that, and when I get out of this texture calculation, we'll go in and I'll show you where you just see it. We'll give you a number of grains that you have, okay? Okay, so for this one, 16, 22, I don't care. Somewhere in here, we're gonna calculate this texture. Let's do 22. No, let's do 16 because that doesn't take as much time. But it should be quick anyway. Do we want to enforce a sample sheet symmetry? I'm going to say no. Let's do no symmetry. We certainly don't have a orthotropic sample symmetry, right? We have an individual growth direction. So I'm turning that off. Do we want to use all measurement points? Do we want to use a certain number of points? Do we want to just look at the average orientation of each grain to use that, right? Usually I use all orientation points because that gives me a good statistics for an area fraction of how many orientations I have there. So I use the entire data set. Say okay. Now this part is telling me what do I want to plot up after I calculate the texture. So this is saying pole figures, inverse pole figures. Let's add an ODF to that. We're going to use Bunge-Euler angles, and I'm just going to do our standard 90-90-90 plot. 90 degrees in phi 1, phi 2, and capital phi. Say okay. We didn't do a Rodriguez vector, but that's an option, right, in the ODF. We could do Rodriguez or these other Euler angles. We could just calculate a fiber. So let's look at a 1.0 fiber, something like that. But let's just do these. Okay, so it's calculating. And that's how long it took to calculate the texture for this one, looking at every single measurement point and figuring out what I have. Now, if I look at the summary view of the data here, this tells me my number of points. Help me. There's the number of points. Okay, tells me how many points I have and how many of those points are good. You know, how many I have good measurements from. So 1,249 data points. Now the definition of my grain is done in the properties of my partition, and the grain is determined here of what the definition is. So it says 5 degrees tolerance angle, and usually I'll put a minimum size of 5 instead of 2 for grains, and that anti-grains is a funny term, whether we want to use confidence index or not, if we want to define it as multiple rows or a single row. So I don't require that. So this is now the definition of my grains. Okay, so that defines what the grain is. If I want to, now I'm answering the question about how many grains do we have. If I want to come in here and just look at grains, one thing that I can do is I can tell it to show grain IDs. He says it does that up to 5,000 grains. Now this isn't something I would recommend, but it's something you can do. So show grain IDs. So now it's going to put a number on each of the grains. Right? And it starts up at the top left and ends here in the bottom right. Whoops, trying to blow this up. So I'm just blowing the data up. So you can see down here the lowest grain, 376, so probably there's 376 defined grains, right, in this data set. And that is based on that definition of 5 degrees and 5 grains together. So if I made a 3 grain, 3 points were a grain, maybe this little one would be a grain, or maybe this little one would be a grain. So you have to determine what your grain definition is, right? If I told it to have 20 points to define a grain, then all these little ones wouldn't be grains. All right. So the number of grains depends on your grain definition. That's an important part. And then You can show the grain IDs. A lot of times what I'll do is I'll just export a grain file, because if I want to look at the properties of each grain and do my own calculations on them, then I'll just export a grain file, and typically I will export a single point for each grain based on my definition. And it will give me the average orientation of the grain. So I can plot all of them out. I know exactly how many I have, right? Or I can do charts that show individual grains. So there's a lot of ways to do it. This is just a real simple way to look and say, this is my grains, okay? All right, so we've calculated a texture. Now we're going to go in and say, let's do a new texture plot. So I'm clicking on the texture I've calculated, going to the new texture plot. First thing it says is which type of plot. So I have an option of a pole figure, an inverse pole figure, and ODF. Let's plot up the pole figures. So there it's showing the pole figures that I have. Showing the maximum intensity here, telling me it's about 14 times random. If I do a orientation space plot, we do this. This is where that fiber goes, where the 001 is rotating, right? So we have a 001 in the transverse direction. If we had it in the rolling direction, then this would be along this side, right? We have it in the transverse direction, so that's showing our texture. Now it says 17 times random, right? Which for a fiber texture like this, you expect approximately the same times random value in the ODF that you have in the fiber texture. That's because all of them are lined up in a certain direction, and you have the orientation uniformly spread in the plane, right? So 100 pointing in the growth direction, and then random 100s in the normal to the growth direction. If I had some kind of in-plane preference, then I would still have in the pole figure, I would still have about the same times random value, but in the orientation space plot, I would have a much higher times random value because it's not uniformly distributed in the plane. So typically, if I have something besides just a straight fiber texture, the times random values in the ODF would be much higher. If it's a straight fiber, then I expect them to be about the same. Okay. All right, then I could also plot up, we plotted inverse pole figures, which we can do if I do it properly. So there's the inverse pole figures for the reference direction, the normal direction, reference direction, and the transverse direction. And the one where I actually see the peak is in that transverse direction. That's the horizontal direction. Did you have a question? Okay, just stretching. Okay. Okay, so now the question was, what about volume fractions? What if I want to know how much volume fraction of 100 I have? Now remember, we're looking at everything in the map. Right, we're looking at all those data points. So we have some that are not part of our fiber, but we're including all. So how much is going to be within a certain angle of what I'm plotting up? There's a lot of ways to do this. The way that I was starting to talk about was, let's just do a new chart, and we're going to look at a crystal direction chart. If I do crystal orientation, it wants to know the complete orientation. It's not talking about a fiber, so crystal direction is talking about a fiber. And we're going to line up, we're going to add, we're going to look at a 001 plane aligned with the 010 direction. Oh, nope, that's crystal direction. So I'm leaving this. Don't mess me up. Okay, 001 plane. In the 010 sample direction. So this is showing the sample direction. This is showing a crystal pole or a crystal direction. Remember, for cubics, they're the same. If there's another crystal symmetry, these would be different. but they correspond to each other. You notice when I put a 1 here, then it showed up in the pole also, right? So it changes it. All right, so we have that. We're saying how many are lined up in this direction. And right now I haven't told it anything specific about where to truncate, so it's just going to show me the entire data set. So it gives me this. So it shows me a little plot, and it shows me the direction. So within 4.1 degrees, I have 21% of my data aligned with 100. If you get up here to 20 degrees, it's up over 80%, right? So that's the volume fraction or the area fraction that I measured of 100 to within a given tolerance angle. So this gives me all the tolerance angles, and I can, you know, if I just play with this a little bit, I say what range, it's going to go 0 to, you know, I can go all the way to the maximum range, or I can go just to 10 degrees out, something like that. So let's leave it all the entire range, but let's say instead of putting that in 20 bins, let's put it in 55 bins, something like this. So now it's showing a smoother curve, and it's giving a lot more specific information, right? Instead of every 5 degrees, now it's showing me data every 1 degree approximately, right? So the value that's listed here, you can think of it as being in the center of your bin, right? So your bin is 1.04 degrees, so it's showing me the value at 0.52, which means from 0 up to 1.04, right? Okay, questions on that one?
So which crystal direction alignment you have to consider?
So this is something you define. The question is, which crystal direction alignment do you consider? This is something you define here. So I've told it I want to look at 001 planes that are aligned. So that's the crystal direction. And they have to be aligned with the y-axis defined by this coordinate frame. Right, so how tightly aligned are my 001s with my y-axis? So the question is, who cares? The question is, who cares, right? That's the question. He said, what's the significance? But the question is, who cares? Right? That's the real question. So sometimes we want to know, you know, we have a strong fiber. Sometimes we want to know what fraction of our material is actually growing preferentially, right? So we have this columnar growth. So what's the fraction of my system that actually is growing in the 001 direction, right? Now, maybe I want to do it as a function of position out. So I can do it like that. Maybe I don't care exactly on volume fraction, and I just want to know the texture times random value, right? So maybe volume fraction doesn't really matter. Maybe I just want to know what's the texture strength in looking at times random, something like that. Okay. But as you're analyzing your data and asking yourself questions about your data, that's how this software was built up, right? As people sitting and asking questions about data and saying, boy, I wish I knew what the volume fraction was. And so, okay, let's put in a tool that does volume fraction. I wish I knew, you know, whatever. And so that's how all this is built up. It's people just doing research and asking themselves questions. So, all right.
So the SPN plane which is aligned with the axis 2 and the direction which is aligned to axis 2.
So crystal direction 001, axis direction here. So this is 001 aligned with the 2 axis, right?
No, it says the UVW aligned with the axis 2. So the UVW direction
Okay, UVW direction.
aligned with axis 2 and
So this is, remember we've asked it to do a crystal direction plot, okay? So you can define a direction over the crystal space, right, over the unit triangle, by defining a pole, which is normal to a plane, or by defining a crystal direction, right? So I can do an HKL, which is normal to your plane, or I can do a UVW, which is a specific direction in your crystal. With cubic crystals, they're exactly the same. So the 001 pole is parallel to the 001 direction, right? So it doesn't matter on cubics. If I go to a different crystal system, these numbers will be different, right? It will give me the direction that's lined up with the specific plane. Okay. So let's cancel that. Let's, yeah, I could just tell it here when I'm playing. I could just tell it, whoops. I could just tell it how far I want this to go, if I want to go 0 to 10 degrees or whatever. So I can zoom way down in on a given part of the structure, right? Now I can also, of course, just do a map if I want. So I'm going to do a new map, and I'm going to say, show me, let's make it color because we like colors, and show me a crystal direction map. Crystal direction. Then I have to identify it again, so I'm going to add the same direction, 001, aligned with this direction. What if over here in the sample direction I put 111 or something? It's not talking about a crystal axis, it's talking about a specimen plane. So it'd say which is aligned with a direction that's consistent with x equal y equals z in your xyz coordinate frame, right? Or E1, E2, E3, however you like to define it. Okay, so we're doing the map. We're saying what's the tolerance? So let's say I want to know what's within 10 degrees. And I'm going to color that in some rainbow, but let's not make a rainbow. Let's do 2 colors. And let's do white to red. Okay, so now I'm going to plot it 0 to 10 degrees. And it's going to be red. And I'm going to say okay. So now that's showing the grains that are lined up within 10 degrees. That's what it looks in the inverse pole figure space, what I'm doing. And now it tells me that the fraction of data is 0.55. Can I read it up there? Nope, I can't read it either place. So 0.558 maybe, or 556, whatever it is. Okay. So now it's showing me what that fraction is within a specific number. And then it's coloring in where those are, and it's shading them according to how tight they are. So these nice red ones, those are pretty much aligned exactly. And nope, it's the other way, isn't it? The way I've plotted it. The darker red's on the outside. So I meant to do it the other way. Color gradient. I'm going to reverse that. This is the minimum, so that's 0 degrees, so that's perfectly aligned. So I want the darker color perfectly aligned. Okay. So now the lighter colors that are here in the map are closer to 10 degrees away. And this is because I'm using a beta version of the software. I get this crap in there sometimes. Okay. Okay, so that's another way just to look at it, right, for orientations. Now we're at 10:45, and this is when I decided to stop, because we're going to be done by 12:30, so we each take an hour 45. But I'll take, if anybody has any quick questions just for this, I'll take any quick questions.
Sir, you have calculated the 0, 1 and 0, 0, one direction.
I've calculated the volume fraction of 001 aligned horizontally, right?
If we calculated the same thing in gamma fiber direction,
Uh-huh.
then what is the
So gamma fiber would be 111 aligned with normal direction, right? So that's the gamma fiber. So any of the fibers you can define like that. You put in sample direction, you put in your crystal direction, and you can get the volume fraction of that crystal. And you can map out exactly where they are. Okay? Others, yeah.
Quick question. The brass component is 110 with aligned to this 001, 001.
For brass is 110, 112.
What?
110, 112. 110, 001 is Gauss component. Mm-hmm. Yeah, so brass is 110, 112. Okay. Others? Okay. We'll try it again tomorrow. I'll leave you back to, are we still in phase field? I don't even know where we are right now.
You're lost, that's what it is.
Oh, we're not lost. We have a good guide.
But if you get some cookies. While I'm struggling. Yeah.
And it is more important than the food.
Yes.
And
Yes.
I initially thought that
No, that was way too much trouble.
I will give the money and they will give it immediately, but it was it was like a sorry about that.
Okay. Does this mean that we are ready?
Yes, sir, we are ready.
Well, I just want to see the slide over there. Yeah. Okay, so we started last time one interesting phase field model which dealt with concurrent melting and capillary flow. That is the flow. So we have a aluminum silicon alloy which melts partially where you have a significant amount of silicon. Aluminum doesn't melt, but the fluid is taken by capillary forces. It's taken away, so the silicon is taken away. Right, it melts here, right at this concentration. Well, and the nominal concentration of silicon is somewhere here, of this alloy, close to the eutectic. So we let's just think, what kind of problem is this? Well, first, this is a problem without stresses, really. Well, without elastic stresses. There will be viscous stresses in a fluid. And this is, as far as I know, first phase field model which deals with concurrent melting and flow. People have done melting, and people have done capillary flow. In fact, we have shown capillary flow before, but to combine two things is, well, I believe new. So this is very much work in progress, and I will show you some preliminary computational results. So we have 4 phases. This is alpha solid or aluminum, right? Almost pure aluminum. Then we have a silicon solid. We have a liquid which is a mix of aluminum silicon, and we have inert gas which does not interact with either aluminum or silicon. And we have 2 concentrations, concentration of aluminium and concentration of silicon. All phase fields must satisfy this condition. That is, they cannot sum up to more than 1. I am only in one phase field or the other, or I have a mixed 2, but that mix has to add to 1. I have incompressibility condition, and my concentrations do not exist in phase phi4, so C1 plus C2 must be 1 when I'm in one of those 3 phases, 1, 2, 3, and will be 0 when I'm in phase 4. That is in the gas. So these conditions will be enforced by Lagrange multipliers. This will be non-capillary pressure. The Lagrange multiplier, which goes with incompressibility condition, always turns out to be pressure. And this is the third Lagrange multiplier. So we write our free energy. Let me start my timer so that I know how long I'm talking. Okay, so we write our free energy as a function of phases and concentrations. And when I write C, I mean both C1 and C2, right? Then I have this gradient term, which we described previously, represents interface energies. But now I have a sum of squares of the gradients, right? And these coefficients kappa 1. And I have interface energy with the solid, right? Which depends on phi, that is, by solid I mean the boundary solid, which in this case, if you recall, was aluminium tube here and aluminum oxide up here. So this is the oxide and this is aluminum tube, this blue one, right? So then when I take time derivative, after some manipulation, I can get that time derivative, well, in the following form: rate of change of phase fields and its conjugates for all phase fields. Then a tensor here, omega I, or for each phase field there is one tensor omega, which will turn out to be what we call capillary stress tensor. This is dyadic product, gradient, dyad, gradient, right? That expands power on the velocity gradient because it's a stress, right? And then I have those partials of free energy with respect to two concentrations. This power conjugate of my phase fields will look the same as before. We had this before if you look at the previous model. So there is nothing new here. Well, that's the free energy. Now, dissipation. Dissipation, to remind you, that's energy transformed from potential energy into heat. And we look at the, we are mostly interested in looking at the peak temperature, right? So we really don't, we really treat this as isothermal process, because any heat released due to dissipation is much smaller than the heat that we put in or take away from the outside. Also, because we ignore changes in volume, thermal strains, and the reason we ignore them because there are no thermal stresses, right? There is no constraint, it's a fluid, it just flows. So the viscous stresses are important, elastic stresses are not important. So volume is the same as mass, mathematically. Okay, so what will be in the dissipation? In the dissipation, we have viscous part, viscous stress doing work on the deformation, well, viscous deformation rate, which will be deviatoric. Rate of change of the phase, melting, solidification, will all have their energy penalty associated with it, and these are both dissipative processes. And then dissipation due to diffusion. Every step in diffusion is a dissipative step. Now here on the boundary, I have the same condition as before. This is what we did when we just did capillary flow. But here for dissipation, I have triple lines and solids. So and gas. Phi3 is liquid, and Phi4 is gas, right? So as they move, they dissipate energy on the solid boundary. So now which phase is conserved here, which phase is not. If I look at a closed system, only my gas phase is conserved. Aluminum and silicon could both be part of the liquid. They can increase their volume, decrease their volume or mass, and they mix with the liquid. So only the phase, only the gas phase will have a flux, and that flux is J, and that flux will be proportional to the gradient of the, so this is conserved phase field. Gas is a conserved phase field. Other phase fields are non-conserved phase field, so they will give us second order diffusion equations, but the one for the gas will be fourth order. And we have boundary conditions. Well, nothing flows in and out. On a boundary delta V, nothing flows in and out. There is no flow of gas, and this is proportional to the gradient, so the normal component of the gradient of M4 will be 0. I have constitutive law for viscosity, where my viscosity now depends on phi. It will be so high for solids that in any appreciable time I will get no viscous deformation. So those will differ by orders of magnitude, right? For liquid, for gas, and for solid. So very small for gas, moderate for liquid. These molten alloys have viscosity comparable to water. And very, very high, orders of magnitude higher for solids. So now, my diffusing my species are conserved. My aluminum, my alpha phases and silicon solid phases are not. But my species, aluminum and silicon, are conserved. So there are mass fluxes or atomic fluxes which have their own potentials, and they are proportional to those potentials, and those potentials are generalized forces who do the work, which expand power on rate of change of concentrations. I'm sorry? Yes. Yes, you have only so much aluminum atoms and only so much silicon atoms. Right, you're not bringing any new in. But the phases, aluminum solid phase is not conserved because it melts, right? Also silicon phase diffuses into aluminum, melts, and that's not conserved either. Okay, so we follow the procedure that we outlined before, and I'm not going to go through that because it's much too painful, right? One needs to do lots of bookkeeping. One writes power balance, and then from power balance, principle of virtual power. Well, power balance simply said that the work, power expended by external forces is equal to rate of change of kinetic energy, rate of change of potential energy, plus dissipation. No mystery there. But then if you write it properly in terms of your independent variables, you can formulate principle of virtual power, and then from there you get your governing equations. And here's how they look like. And I nominally assign governing. You must have as many differential equations as you have variables. So for bookkeeping, I assign equations to variables, but they're all coupled, right? So the 4 equations of motion, which deal with variables, velocity vector and a pressure scalar, that's 4 scalar variables, are this modified Navier-Stokes. Now, this, and this, and this. This is all standard Navier-Stokes, well, fluid mechanics. These are capillary stresses. Notice that there is a contribution for all phases, but anywhere where this term exists, you will have mostly two phases will be two terms of this sum will be zero, except at those triple junctions, right, well, when they meet. But within pure phases, this term doesn't exist. And incompressibility condition. Corresponding to those equations, there are boundary conditions in terms of shear stress in the gas, right? Because your boundary might include solid and gas boundary, for example. So on gas boundary, shear stresses will be zero, and pressure gradient is rho g. On solid boundaries, well, such as here, we have no slip, no penetration condition. So, because we keep our solid boundary fixed, velocity of fluid there is zero. Three differential equations corresponding to phase fields, to three condensed phase fields, and there is a fourth one for gas. So those three are second order. These are Lagrange multipliers here. And I have diffusive motion sorry, let's first do the fourth equation. Fourth equation is fourth order diffusion equation. Remember, this M4 had Laplacian of phi4 in it, right? So it will be fourth order in phi4. Now boundary conditions on gas boundary, my computational cells, I cut through gas. I can do that. Those phis are zero. Sorry, phi4 is 1. This is a mistake, sorry. It's 1, not 0. But on solid boundary, for phi3 and phi4, I have this diffusive boundary condition. And also I have this function gamma on the solid boundary, which changes from gas to liquid. Gas was phase 4, liquid was phase 3, right? So it depends on phi3 and phi4. That's interface energy between my solid boundary and whatever is inside my domain. I have two diffusion equations, but not they're not both necessary, right? Because I have that condition, if you recall, that C1 plus C2 must be always equal to phi1 plus phi2 plus phi3. So if I'm computing those three, I don't really need to compute C2, right? I can only evolve C1, and C2 will be this minus C1. Okay. And then I have, yes, here's M4, sorry, I forgot that I have it here. So when you substitute M4 here, right, that's the fourth order Cahn-Hilliard phase field equation. So for Lagrange multipliers, lambda and he, I have two partial differential equations which are not time dependent, right? Well, they are, because those terms, those m's are time dependent, but they don't have time derivatives here, with appropriate boundary conditions, right? And this is my M4 if you want to write this as a 2 second order PDEs rather than 1 4th order. Okay, so rather nasty system of equations, but it is correct. It is thermodynamically and mathematically correct. So let's look at a simple test example. Does it work? Silicon particle inside aluminum matrix. So we heat, well, this way we get a diffusion and as concentration of silicon increases, you get a liquid phase. Liquid phase here is red, and these are mesh artifacts, right? So this is a test run, so we did a very coarse mesh. This should be circular, really. But you see how things are melting around silicon. This is, inside is silicon, outside is aluminum. And I think here we, this outside is aluminum plus maybe 10% silicon. So we need just a little to add to get to the eutectic. That's the lowest temperature where things begin to melt. Sorry? No, this is a silicon phase is red. Everything that is not red is not silicon phase. Here liquid phase is red. Well, in this column, everything that is not red is not liquid phase. No, we don't start from liquid. Red is the liquid phase. So okay, for some reason the well, software gives here well, 0 value. Well, this is before the start, right? This green is an error, right? This is, well, I don't know what this is, but this is what happens with silicon. Silicon shrinks, and you have melting around. That's the point here. Here, yes. Well, silicon also diffuses through the liquid, and gets into the more. So this liquid here. Okay, where is my? Here's my cursor. So this red liquid is eating equally silicon, not equally, but it's eating both silicon particle inside and aluminum outside. So, but the point is we are somewhere at this temperature, right? So only the alloy with this composition can melt. So you need to diffuse silicon into the alloy to melt it. This is about 12. A little bit more than 12. 12 point something is this, I think, is eutectic decomposition. And okay, well, total mass fraction of silicon in this sample is 1.5, right? So we start somewhere, well, with the composition somewhere here, and we heat it up, silicon diffuses, and until it gets, well, to this composition, and then it melts.
Again, the blue one is aluminum. The blue one is aluminum.
Here,
Yeah.
here it's aluminium, but in every next one it's both aluminium and liquid, right? So here red phase is silicon. Everything that is not red is not silicon, right? So you have to look those in parallel. Here red is silicon, here red is liquid, right? These are, well, corresponding times, right? You have silicon, liquid, silicon, liquid. Okay?
This side is silicon liquid and here it is silicon solid.
Yeah, yeah. This is silicon is red, and here liquid is red. Melt. Okay. So now we try rather simple-minded well, simulation, well, of this configuration. Getting, well, anything realistic would be very expensive computationally. You need lots of grains, lots of phase fields. Each grain has to be its own phase field. So in real simulations, we start. There will be many variables phi1 and many variables phi2. So each grain would have its own phase. So we'll have variables phi1,1, phi1,2, and so on. And here phi2,1, phi2,2. But we start first, well, in a simple way, with a single variable for, well, why do we need that? We need to separate those phases. But first, we start with easier runs, right, computing runs, and we put silicon lamellas, these are dark grain, around aluminium grains. So this says gas. Gas is up here. This is just so this is all gas, and these are aluminium alloy walls. Tube. So here's how the flow proceeds. Liquid is red. You see the melting around silicon, and it uses up that silicon fairly quickly, except this one at the bottom, right? So this was just a test run. We wanted to see how our flow and melting is working. Then, well, somewhat different run with silicon in form of circular or spherical. This is all 2D, right? So circular inclusions and some bubbles of gas. So when we start melting, here's your liquid forming here, and then liquid grows. And some of those liquids percolate, and then you have, well, capillary forces pulling down. See here. Others don't percolate. So this will not flow because it has not turned into granular material. We would have to, what really we need to do, and that's the next stage, and I'm looking for a graduate student to do that. We would need to put silicon lamellas in between the bubbles, and then we would get percolation, right? And unmelted grains would remain. Around will be liquid, but that again, this is work in progress, and this has been done by my former student who has graduated, and this is the same student that is first author on that paper that I gave you last time, Sasha Kovacevic. He's at Oxford now as a postdoc. So I'm looking for a new student to continue this work. But the point is, model is working. We just need to do proper computational setup, well, in the beginning. Now, let me introduce you the last problem. We are going to deal now with a model which describes sintering and creep. I have already introduced you to what our main motivation for sintering is. For creep, well, you know what the motivation is. We need to model creep. We need to understand how polycrystalline materials creep. But this is additive manufacturing, 3D printing of, if I remember well, this was silver. So nanoparticles of silver, so particles are about 30 nanometers, average size, are printed, they're embedded into gooey polymer ink, right? So they're printed with a print head to form needles which are about 20 to 50 microns thick and several millimeters long. These needles are needed for brain testing and brain surgery. They are so thin that they plan to insert them in the brain and do some diagnostics during surgery and maybe outside surgery, but they need to be straight, right? Except that once you print, you need to sinter them, right? As you heat it up, first you burn out the polymer, and then you start sintering. And when you start sintering, this thing opens up like a flower, and then partially comes back. So if you look at the curvature, time history of curvature looks like this. You get a peak curvature. This is a temporary curvature, and then you have a final curvature, which is never corrected. Now, first thing we have observed here is that temperature is higher on the outside. Why is that? That's whole another story. It has to do how the thing is heated. It's very difficult to control temperature precisely, but there is a significant temperature difference between outside of this array and inside until the last stage. Well, to make things simpler, we try that with walls of different thickness, and the thinnest wall bends the most, the thickest wall bends the least, but we have the same pattern. We have a permanent curvature, we have peak curvature, and then, permanent curvature. So, and also we measure temperature, and it's always things always bend towards hotter side. So for this particular wall, the inside would be hotter and outside would be colder. Now, it's sintering, And so if you measure, well, if you section the final sample and measure porosity, you can calculate how much curvature should you get from the gradient in porosity, right? And well, if you plot observed curvature against curvature predicted by the porosity, these are our experimental points. So, well, one of them even has opposite sign. Essentially, the curvature is not due to the change to the gradient in porosity. Gradient in porosity is so small that it will not produce any curvature. So there must be a mass transport mechanism, because in the end you only have voids and you have a solid mass.
It will be the porosity is higher on one side, on the outer side.
From our experiments, there is no gradient in porosity. It's negligible. So you have to transport mass, right? Because if one side is to stretch or shrink more than the other, you can either have more voids or more solid mass. And the only way to get more solid mass is to transport somehow mass. So these are repeatable experiments. So well, our motivation here is we want to find out how is that mass transported. Well, one option is we call particle squeezing. So if you have say two bigger particles and temperature here is higher, so those two particles sinter more, they push this smaller particle towards lower temperature, right? The other one is bias diffusion, right? Because on each contact we have those stresses. This is a surface tension. This is a stress which must equilibrate this surface tension, because keep in mind there are no macroscopic stresses here. You only have microscale stresses which are not self-equilibrating, but they equilibrate with surface tension. Sorry? Did you say gravity? No, this is all this is so small and so light. In fact, this paper has been published in Nature Communications. Well, one of the reviewers insisted that we do calculations about gravity. So we've done I've done calculations. Gravity really does nothing. It's completely insignificant with all the other forces. Surface tension is orders of magnitude larger than gravity here. So, but we don't know which mechanism operates, and that's why we need to formulate phase. Right, you cannot observe sintering process in situ, right? It's in a furnace, and it's on small scale, so you would need to somehow to fit your SEM into the furnace, right, to look what's happening. And even that, most of it is hidden. You could only look at the surface, right? So the only way of discovering what is really happening here is to develop a model. Now, let's see, what do we have in this model? We have diffusion through the bulk, through and over surfaces and interfaces. We have lattice growth at interfaces and boundaries. We have microelasticity. Grains could slide. So that's very much like creep. Mathematics of this is the same as mathematics of creep, except that in creep you would put additional external stresses, right? And here you, well, in sintering sometimes we use stress-assisted sintering. But the point is we are dealing with solids, and for both sintering and creep, we need to consider lattice lattice continuum. Okay, so let me just remind you of what lattice continuum is. We say the material which moves with the velocity v is lattice. Now, by mechanism of diffusion, atoms come to one side and build a new lattice. So you have motion of the lattice, but then you have additional motion of the boundary with respect to the lattice. Lattice growth and lattice disappearance. And we talked about that. I'm just reminding you with this slide. So how are we going to represent that? Let's first think of a sharp interface model. Let's say I have two domains, I and j. So the normal velocity of I plus lattice growth of I is equal to the normal velocity of j plus lattice growth of j. So if you want to write it this way, right, the total lattice growth will be g. Now, sliding, if my boundary normal is n, then I can formulate a tangential projection tensor, P, which is unit tensor minus dyadic of n's. So let me just give you some intuition for this. This is a unit tensor. So this is 1, 1, 1 components. Now, this dyadic, let's say that if n corresponds to x3, right? So this n will be 0, 0, 1. Sorry, 0, 0, 0, 0, 0, 0. Right. So my P will be 1, 1, 0, 0, 0, 0, 0, 0, 0. So the property of this rank 2 tensor is that when I multiply any arbitrary vector in space with P, it gives you the now this is a rank 2 tensor, this is a rank 1 tensor vector, so the product is a vector, but this vector now lies in the plane of P, in the plane that is normal to n. So so the tangential velocity of grain I plus slip between grains I and j is equal the tangential velocity of grain j. And this S could really be anywhere in the plane. Now, how do we translate this in the language of the phase field diffuse interface model? That's a bit of a longish story, but it's fairly intuitive. You may want to read either one of those publications here to see. Basically, you have to spread that growth throughout the interface region, which means that the growth should exist only when your gradient is non-zero. And you also spread the slip throughout interface region. So they both exist when the gradient of phase field is non-zero. It's a little mathematical trick, but you can see the details in those publications. Okay, so I have been talking for about 45 minutes. Let's make, well, 5 minutes break, and then I will deal with this last model and show you the results. But, well, I want you to refresh before we jump into mathematics. Okay, so before I continue, are there any questions about anything that I talked about previously? Either about this model which deals with melting and flow, or about motivation for what we are going to do now, or anything from previous lectures. Okay, so this model that I'm going to describe now is for creep and sintering, but it's also for grain growth, recrystallization. It's all there, and it is this is what we're going to use to model our behavior of triple junctions, which is the part of, well, of the research project which we are planning to conduct with Somjit and co-workers here at Kharagpur. So let's see. We have solid grains, and let's say we have n grains. Each grain is its own, and I'm going to look at very simple case where I have a single species. It is not very difficult to add multiple species to diffuse multiple phases. That's matter mostly of bookkeeping. But conceptually, you can deal with a single phase, single species, single crystalline structure, right? But each grain is a different phase. So I have grains, which I will denote with capital Phi, and I have gas, which is Psi. So Phi is the sum of small phis, right? And Phi plus C is 1. So, okay, what do I need to describe? Solid phases and gas void phases, well, that's it. I will have to deal with diffusion. I will have to allow each lattice to grow. Now, each crystalline lattice for one grain is a phase, so each phase can grow. Phases are not conserved here. But the driving forces for that growth will depend not only on interface energy, but also on elasticity, that is, on stresses, and composition, because composition creates its own eigenstress. Well, it creates eigenstrain, but because grains are constrained, that creates eigenstress, and stress drives diffusion. I need to allow for grain sliding, but to have lattice grow or disappear, I need a lattice source sink description. So let's just do the basics. First, I have my velocity gradient. Now, if you recall, for lattice continuum, I don't have reference configuration, right? If this grain, right, if this is my grain originally, and then it has, this piece of lattice has grown, this is new lattice here, I don't have any reference configuration for that lattice. I have to invent it. But if I have followed my deformation gradient through time and solved for my velocity gradient, I can integrate deformation gradient in time, and I can formally define reference position of this newly formed lattice, because my f represents, right, my tensor f maps d capital X into d small x, right? D small x is a current position, that, but I can do the inverse and get and integrate this to get my reference positions x formally. But I need to follow this f, and f is I will denote its determinant with a italic f. So let's CV be number of vacancies per lattice site. So this is vacancy density per site, per lattice site, and CI number of, well, interstitials. We don't have to deal with interstitials, but we can put them all together and define new concentration variable 1 minus CV plus CI. Let's call it eta. So, well, in my reference configuration, that is unstressed configuration, I have n bar lattice sites. In stress configuration, I have 1 over f by n bar. And Qn is flux of solid atoms relative to lattice velocity in the current configuration. Okay. Now, this is important. My velocity gradient will consist of, this is elastic, and let's not deal with plasticity. So no dislocations, no dislocation climb, no dislocation glide. So just crystal, diffusion, elastic deformation, and the growth of crystal. So this L star is elastic compositional, meaning that it will include compositional eigenstrains. And this is grain boundary part, which will exist only when my gradient of phase field is non-zero. And you'll see how in a moment. For deformation gradient, I have multiplicative decomposition. That is, I imagine that I first grow the lattice and slide on the boundary, and then I deform elastically compositionally my material to make it compatible. So there is a slight complication here with geometry. L star and L star will be simple, but LG will be a little bit more complicated. Those who dealt with crystal plasticity are familiar with this. But I remind you that this LG, this component, is not zero only where gradient phi is different from zero. That is at grain boundaries. At that thin layer, our interface layer, where the gradient is non-zero. So I can write my interface normal as unit normal. So gradient of phi divided by absolute value, and I want it to be outer normal to domain I. So phi is 1 in domain I, so its gradient will be pointing towards the domain, right? It's 0 outside domain. So I'm putting a minus here, right? And then I have a tangential projection tensor, P. So I will define my boundary growth rate as G, and my boundary slip rate as for each grain SI equals minus Sj. So SI is how much grain I slips with respect to grain J, and Sj is the vector which tells you how much grain J slips with respect to grain I. So there are different ways of describing that. So my LG will be G on the diadict NN, right? That's a diadic for boundary growth, and my slip vector, my shear strain at the boundary, at the thin layer, will be S dot Ni, and this should be sorry, Si. There is an error here, I'll have to correct it. Si Ni. And I am putting 1/2 here because I'm counting all the grains, so each one of those is counted twice, right? So 1/2. One can derive a diffusion equation in this form. This is diffusion flux in reference configuration. That's why we have F star here. This is the boundary grown. This part is a sink, right? So rate of change of eta, eta increases proportional to the negative divergence of flux. That's the usual transport. But I also have a sink. My boundary grows takes atoms that are diffused, right? So instead of increasing the concentration of atoms, those atoms are spent on new lattice planes. So this operates as a lattice sink, as a eta sink. Sorry? Yes. That's the rate of growth. See, well, if this is your grain, right, and that let's assume that that grain is moving like, well, as a rigid body V, right? Well, in addition to that V, this boundary may be growing at a rate G, and if this is it's normal, right, your n, the total velocity of any point of this boundary is n dot v normal velocity plus g, right? That would be normal velocity, right? So boundary grows with respect to the lattice. Yes. So it builds new lattice planes, right? Eta is well, combined concentration variable. Here it is. 1 minus C vacancies plus C interstitials. Well, we can forget. Well, think about vacancies. Sorry? Eta, this, yes. Yes. Eta dot is the rate of change of eta.
The rate of change of the concentration.
Yes, yes. So this eta dot, if you think well, of diffusion of vacancies, eta dot is just minus concentration of vacancies, dot. Well, time derivative. Any more questions?
It is interstitial or the lattice?
For the purposes of this model, we are dumping both vacancy vacancies and interstitials into one diffusion variable, right, concentration variable. You don't have to do that, right? But just to keep it simple, you can have different mobilities for interstitials and vacancies. You can look at them separately, but that increases the number of variables. And well, in the bookkeeping,
Vacancy is the lattice vacancy or the interstitial vacancy? The vacancy is
oh, lattice vacancies. We don't consider interstitial vacancy. You have well, interstitials come on the top of your lattice, right? And vacancies come as a subtraction from lattice. Now, of course, if you have complex lattices, multiple elements, you can look at it differently. But that's purely matter of bookkeeping, right? So I'm developing here a very simple model, simplest possible model. Okay. So, well, the procedure is the same, except that here there is no. We will ignore gravity, so no body forces, and we will ignore dynamics, inertia. Right. So these are quasi-static processes. So the power expanded by external forces, tractions, translates into rate of change of potential energy or free energy plus dissipation rate. So free energy, chemical, elastic. And then I have the usual interface terms for phase field, right? All of those phi's, and I have those coefficients kappa and zeta. And there is there will be something on the computational boundary, on the boundary of the domain. But let's not drag that now. Things are complicated enough without that. So, if I do time derivative, I will get that some stress tensor, which I call sigma hat, does work on my velocity gradients or my deformation rate. This stress is consists of elastic stress. This is stress that which is conjugate to elastic strain. So my total stress is elastic stress plus those capillary stresses, which come from well, surface tension, but more complicated because these are tensors now. My diffusion flux, yes, my diffusion flux will have a conjugate m naught, well, potential energy conjugate m naught, which is just rate of change of f with respect to eta. Rate of change of total energy density with respect to eta. And my phase field potentials, mu and m script, look like this. Partial of energy plus minus Laplacian term, and here partial minus Laplacian term, as usual. Now, my lattice growth, G, will have energy conjugate G naught, which will consist of a stress projection. This is a normal stress on the boundary. And this is the rate of change of energy. So why two terms? Clearly, normal stress on the boundary does work on lattice growth. But to produce that growth, you're creating new lattice with new energy, right? So there is a price to pay for that, and that price is denoted here. My slip will have a power conjugate or energy conjugate S naught, which is just this is just a resolved shear stress, but it is resolved to the direction. Well, it's resolved to the plane, but it's a vector, right? It's not resolved to a particular direction. It's a shear stress vector in a plane. My dissipation will consist of, well, power conjugate, dissipation conjugate on flux, on rate of change of phases, mu and mu I. This is viscosity, and this operator, this is 1/2 V del. Well, let me write it. This is deviatoric and symmetric velocity gradient component. Because we want to consider our gas as incompressible, and I have dissipation both through lattice growth and lattice sliding. So I will say that my lattice is proportional to lattice growth is proportional to its well, power conjugate, and my S slip vector will be proportional to the shear stress in the plane. Okay, I need to deal with interface diffusion, and I can do that using those tangential projection vectors, but for an interface. So for an interface between two grains, I can write a normal which is now neutral with respect to order of the grains, phi j gradient phi j minus gradient phi I, and so on and on. And on the solid gas phase, I could just do the projection with a gradient of gas phase variable, and then I will have a bulk mobility. I will have grain boundary mobility, and I will have grain surface mobility. So instead of mobility parameter, I have a mobility tensor for my flux of atoms. This is a power conjugate, this is the flux, this is mobility tensor. So procedure is the same as before, principle of virtual power. I did not do that in time. So that's not useful now. But we are close to the end. This is the last equation slide, so bear with me a little bit more. So these are my equations. From Cauchy's equation of motion, the only part that remains is divergence, but it's divergence of the total stress. We drop out inertia because everything is very slow, quasi-static process. We ignore, well, gravity. Other forces are much more important. So it's a quasi-equilibrium, divergence of total stress. And total stress is elastic, viscous, and capillary. Okay. These can be, both of those can be expressed in terms of F and V, right? I need evolution equation for F star, and this is my velocity gradient, total velocity gradient with the with lattice growth and slip, right? Evolution of my diffusion variable has a gradient, divergence of a flux, and it has a sink term. This is lattice growth, is the sink of mass, right? You need to sink of atoms, because you need to put atoms into the mass, into new lattice. My phase fields, and this is the form which you obtain when you eliminate Lagrange multipliers, which impose those boundary conditions, those overall conditions that sum of all the phases is 1. So B is the mobility parameter, number of grains, mg, and these are potentials for each grain, which we have defined previously, and this is the potential for the gas phase. To define this G and this S, I have constitutive laws. G will be proportional. Okay, where is it now? I need to find where is my. Yes. This is the G is a state variable, which has this evolution law. S will be power law. That's one simple way of where S yield is a threshold, boundary yield. And this capital S is the projection of the stress to the plane. The functions F and epsilon is elastic strain, and it is quadratic form of epsilon is elastic strain energy, and it is quadratic form of elastic strain, and elastic strain is total strain minus eigenstrain, and eigenstrain has to takes care of the say vacancy and interstitial concentration. This is Vegard's law. So if you put an extra atom into the interstitial space, you increase the volume. If you put an extra vacancy, you shrink it. Now, this chemical energy will consist of chemical energy of solids and fluids weighted by phase field, and their transitions with these double well potentials, which I should not have called G's. These G's are different G's. So these are simply those double well potentials, right, which look like this. We've seen pictures of that before. 0, 1, and at 1/2, they have this value delta F, right? So let's see what those equations are telling us. Let's try sintering, and here I don't have slip. This is a first version of the model which we tried on sintering. This is a bunch of particles in B2 configuration, which is like BCC, except that in the center of the body particle is smaller, so that they all fit, they all touch. And there is a temperature gradient. So we let them sinter. And this is mostly surface diffusion working. We let them sinter. And then we ask whether center of mass has moved, right? Well, there is a net motion of mass towards the right here, and it is given here. Whether that's enough and whether we still have to determine that, but you see that particles on the left are sintering more than particles on the right. Then let's try creep. 2 grains under tension, my velocity, if this is axis 1, this is velocity v1, right? So this velocity will have to have a jump right here, right? So velocities are negative, right? Because this side is fixed. This is a symmetry axis, right? So all velocities are negative. I should plot them this way. So this point, I have a linear velocity, right? Everything is moving, shrinking in grain 1. And then I have a jump here because of the lattice shrinking, right? Here I'm losing lattice, and here's the jump, and that jump increases with time, and then I'm again I have a linear growth, in velocity to the other boundary. So my lattice growth boundary condition is working, and here's one more example to test our model on a physical example. 4 grains, and look what happens with quadruple boundary. Quadruple point. Dave, here's the quadruple point. So it's unstable. So we are still, yes, I'm also looking for a student for this to do. Graduate student willing to do his PhD on this.
So these models are like material specific or for general?
They are
Material specific or in general?
Oh, these are general models. The diffusion and creep. This could be metals. This could be ceramics. The model that I have presented here is for single species of atoms, right? So yes, it is fairly easy to expand it to multiple species, and also to multiple crystalline structures. That can be done. It's a matter of bookkeeping. There are no conceptual problems there. But we want to first make sure that this runs for a single species. Yes, yes. No. Or, one could have self-interstitials. Okay? All done. Lunchtime. Thank you.